Before we begin tonight, I want you to do something small, something that will only take a moment. Look at your hand, not quickly, really look at it. The lines in your palm, the texture of your skin, the particular way the light in this room, wherever you are, falls across your knuckles right now. Now think about this. Every atom in that hand was forged inside a star. Not a star that exists today, a star that lived and ended billions of years before the Earth existed. A star that burned for millions of years and then released everything it had made in a single catastrophic moment, scattering the elements it had built across the surrounding space. Some of that scattered material drifted for a very long time, cooling, moving slowly through the dark, until eventually gravity gathered it along with the scattered remains of many other stars into a new cloud. And from that cloud, a new star formed, our sun, and around it the planets. And on one of those planets, eventually, the particular chemistry that became you. You are made of stars that died before the Earth existed. But here's the part that most people never hear. Those stars, the ones whose material eventually became, you were not scattered randomly through space. They were part of a structure, a vast, ancient, almost incomprehensibly large structure that was already taking shape in the first moments after the universe began. A web, the largest thing that has ever existed. And tonight, we're going to find out what it is, where it came from, and why, once you understand it, you will never be able to think about your place in the universe the same way again. Tell me where you're listening from tonight, and what time it is where you are. I love knowing that this story is landing in different corners of the world, all at once, while everything else is quiet. Get comfortable. We're going a very long way tonight. What is the cosmic web? The largest structure that has ever existed. There's a particular problem with trying to describe the cosmic web, and I want to be honest about it up front. The problem is scale. The human mind evolved to understand things at a certain range of sizes. The size of a hand, the size of a room, the size of a building, a city, a country, a planet. At the upper end of what we can genuinely feel, not just think, but feel is perhaps the size of the Earth. Something large enough that you've never seen all of it at once, but small enough that you can, in principle, hold it in your imagination as a single object. Beyond that, things get difficult. The distance to the moon, the distance to the Sunday, the distance to the nearest star, these can be expressed in numbers, and we can work with those numbers mathematically, but almost no one truly feels them. They're too large. They exceed the range of the intuitions we were built with. And the cosmic web exceeds all of that by a very, very large margin. So I'm going to try something different tonight. I'm not going to give you numbers first, at least not at the beginning. Instead, I want to build the picture slowly, starting from something you can feel and expanding outward carefully, step by step, until we arrive at something that, by the end, might be the largest single idea your mind has ever tried to hold. Let's start with where you are. You're in a room. The room is inside the building. The building is in a city or a town or somewhere less populated, but it's somewhere with a location that can be described by coordinates that sits on the surface of a planet. That planet, the one whose surface you've spent your entire life on, the only world any human being has ever lived on, is not particularly large in the context of what we're going to discuss tonight. It's about 12,000 kilometers across. Significant to us. Almost nothing in what's coming. Above you, the atmosphere thins and eventually gives way to space. In that space, close enough to see clearly on a clear night, is the moon. Then, much further, the sun, along with the other planets that orbit it, and the vast halo of icy bodies that makes up the solar system's outer edge. All of this, everything from the ground beneath you to the furthest reaches of our solar system, is barely a speck in the context of what we're building toward. Past the solar system, there are other stars, hundreds of billions of them in our galaxy alone, some similar to our Sun, some much larger and much brighter, some dim, cool, small, burning their fuel so slowly that they'll still be shining long after the current age of the universe has ended. Our galaxy, the Milky Way, is a structure of these stars, bound together by gravity, slowly rotating, a flat disk, roughly 100,000 light-years across, with a dense bulge at the center and spiral arms extending outward, in which most of the galaxy's star formation has occurred. If you could travel at the speed of light, the fastest speed possible, beyond our galaxy, other galaxies, many other galaxies, the observable universe, the part of the universe from which light has had time to reach us, contains an estimated 2 trillion galaxies. 2 trillion. Each one a structure of hundreds of billions or hundreds of trillions of stars, each one separated from its nearest neighbors by millions of light years of mostly empty space. 2 trillion of them. And these galaxies are not distributed randomly through space, scattered evenly in all directions like stars in a clear night sky. They're clustered. They form groups and clusters and superclusters, structures of increasing size and complexity, held together by gravity, shaped by forces that have been operating since the very beginning of the universe. And all of these clusters and superclusters are connected, embedded in, threaded through by, organized around the cosmic web. The cosmic web is the large-scale structure of the universe, the architecture of everything. It consists of vast filaments, threads of matter, mostly dark matter, but also ordinary matter, stretching across hundreds of millions of light years in nodes where these filaments intersect, which are the locations of the largest concentrations of galaxies in the universe. And between the filaments, enormous voids, regions of space so empty that they make ordinary outer space look crowded. The overall structure, when visualized, and it has been visualized, using enormous computer simulations and observational surveys of the actual universe, looks remarkably like a web, like a three-dimensional foam or a sponge, or the structure of a neuron under a microscope, an intricate network of threads and nodes surrounding vast empty bubbles. The largest filaments in the cosmic web are among the largest structures ever confirmed to exist. Some stretch for hundreds of millions of light years. A few are measured in billions of light years long. A structure that, if you could travel at the speed of light, would take billions of years to traverse. That is the thing we're talking about tonight. The discovery nobody expected, how we found the invisible architecture. For most of human history, the question of how galaxies were arranged in space didn't really arise. Not because people weren't curious, they were, but because the tools to even begin answering it didn't exist. You can't observe the large-scale structure of the universe with the naked eye, or even with early telescopes, because the scale is simply too vast and the light from the most distant relevant objects is too faint. It wasn't until the 20th century, and specifically until astronomers began systematically measuring not just the position of galaxies in the sky, which direction they appeared, but the distance, how far away they actually were, that anything like a three-dimensional map of the universe became possible. Measuring distance in astronomy is one of the harder technical challenges the field has ever faced. Looking through a telescope tells you where something is in terms of angle, which direction, but not how far. Two objects can appear side by side in the sky and be separated by hundreds of millions of light years of actual space. The solution came in pieces, over decades. Certain types of variable stars that pulsate at rates related to the true brightness, meaning if you can measure the rate, you can calculate how bright the star really is, and from that, how far away it must be to appear as dim as it does. Certain types of stellar explosions, supernovae of a particular kind, that always reach roughly the same peak brightness, making them reliable distance markers across vast cosmic distances. Slowly, painstakingly, galaxy by galaxy, astronomers began to build the third dimension into their maps of the universe. And what they found when the three-dimensional picture started to come together was not what anyone had expected. In the late 1970s and early 1980s, a team of astronomers conducted one of the first systematic surveys designed specifically to map the distribution of galaxies in 3 dimensions. The work was slow, every galaxy required its own careful measurement, and the measurements were made one at a time with equipment that would seem primitive by contemporary standards. But as the data accumulated and the maps began to take shape, something unexpected became apparent. The galaxies were not distributed randomly. They were not scattered through space the way stars are scattered through a galaxy roughly uniform, with local variations but no overarching pattern. Instead, they appeared to be concentrated along structures, lines and surfaces and walls, regions where galaxy density was high, surrounding regions where galaxy density was very low. The researchers described what they were seeing as filaments and voids and walls. Plus, it was, at the time, the largest known structure in the universe. It would not hold that title for long. As surveys improved in scope and sensitivity, mapping more galaxies over wider areas to greater distances, the picture continued to develop. The Great Wall was not an isolated feature. It was part of something larger. That larger structure was part of something larger still. The more of the universe was mapped, the clearer it became that what the early surveys had glimpsed was not a local accident, but a feature of the universe at the largest scales. The cosmic web wasn't a hypothesis that was confirmed. It was a structure that was gradually, incrementally, somewhat reluctantly recognized as more and more data made it harder and harder to interpret the distribution of galaxies as anything other than a coherent, vast, organized architecture. The name itself, the cosmic web, reflects this organization. It's not a metaphor used loosely. The actual structure of the universe, at its largest scales, genuinely resembles a web, filaments connecting nodes, surrounding empty regions in a pattern that repeats at different scales across the observable universe. This is not what the earliest cosmologists expected to find. The universe was not supposed to look like this. And understanding why it does look like this turns out to require understanding something that, until the 20th century, no one even knew existed. The invisible architect, dark matter, and the scaffolding of everything. Here's something that I want to be careful about, because it's one of those ideas that sounds simple on first hearing, but becomes stranger the longer you sit with it. Most of the matter in the universe, the vast majority of it, is invisible. Not invisible in the way a distant star is invisible from here too far away or too dim to be detected without instruments. Invisible in a more fundamental sense, it emits no light at all. It doesn't glow, doesn't reflect, doesn't absorb light in any way that would allow us to observe it directly. This invisible matter called dark matter, not because it's dark in the way a dark room is dark, but because it's dark in the sense of being unknown, undetected, unseen, makes up roughly 27% of the total energy content of the universe. Ordinary matter, the matter we're made of, the matter stars are made of, The matter that makes up every object any human being has ever touched or seen makes up only about 5%. 5%. The rest is dark matter and dark energy, a different phenomenon we'll come back to later. The universe is 95% composed of things we cannot see, and only 5% composed of the things we can. We know dark matter exists not by detecting it directly, but by observing its effects on the things we can see. Galaxies rotate in ways that can only be explained if they contain far more mass than the visible stars and gas account for. Clusters of galaxies bend the light of objects behind them in ways that only work if those clusters are much heavier than their visible components suggest. The large-scale structure of the universe, the cosmic web itself, would not have the shape it has if matter were distributed the way ordinary visible matter is. Something invisible is holding galaxies together, holding clusters together, and most relevant to what we're discussing tonight, providing the scaffolding along which the cosmic web is built. The cosmic web, in its deepest sense, is a dark matter structure. The filaments, the threads that connect galaxy clusters across hundreds of millions of light years, are not primarily made of galaxies or stars or gas. They're made of dark matter. The galaxies and gas that we can observe are embedded in the dark matter structure, the way beads might be strung along a thread, present, visible, but not the thread itself. The thread is dark. The scaffold is invisible. The architecture that organizes everything in the universe at its largest scales is built from something that no instrument anywhere in the world has ever directly detected. We know it's there because of what it does, because of how the visible universe behaves in its presence, because the large-scale structure of the observable universe, when simulated on computers using the laws of physics and including dark matter, looks exactly like what we actually observe. And when the same simulations are run without dark matter, looks nothing like it. The invisible thing is real. We are certain of this in the way science can be certain of anything through independent lines of evidence from different methods and different observations, all pointing to the same conclusion. We just don't know what it is. Dark matter is one of the great open questions in physics. Many candidates have been proposed, hypothetical particles that might have the properties needed to produce the effects we observe. Experiments have been designed and built specifically to detect these particles, placed deep underground to shield them from the noise of cosmic rays. Enormous detectors filled with exotic materials, waiting for the tiny signal of a dark matter particle passing through and occasionally interacting with ordinary matter. So far, no confirmed detection. Dark matter remains invisible, unknown, and almost impossibly influential. It is the architect of everything large in the universe, and we still don't know what it is. The filaments, threads across the void. Let me try to describe a filament, not with numbers at first. Numbers will come. But first, just the image. Imagine a thread of material stretching between 2 points. Not a thin thread, a wide, diffuse, enormous thread, more like a river of matter than a strand, denser in some places, thinner in others. Wider where galaxies have clustered along it, narrower in the spaces between those clusters. Now make that thread hundreds of millions of light years long. Now make it one of many, hundreds, thousands, connected to each other at nodes where they intersect, forming a continuous network that extends across the entire observable universe from one end, as far as our instruments can see, to the other. That is a filament of the cosmic web. Along these filaments, galaxies form preferentially. The density of matter is higher along the filaments than in the surrounding voids. Not enormously higher in most places, but high enough that gravity operates differently. Gas collects, clouds form and collapse, stars ignite. Our own galaxy, the Milky Way, with its hundreds of billions of stars, its spiral arms, its ancient core is embedded in a filament of the cosmic web, not at a major node, not at the center of anything particularly dramatic, just somewhere along a thread in the vast network, which means that the star you orbit, the planet you live on, the room you're in right now, all of it is sitting inside one of the longest structures in the observable universe. The filament you're in stretches for hundreds of millions of light years in both directions from where you are. You are inside the architecture. The filaments were predicted before they were observed. In the 1970s and 1980s, computer simulations of cosmic structure formation, starting from conditions just after the beginning of the universe and running forward in time, applying the known laws of physics, repeatedly produced the same result: a web-like structure of filaments and voids. The simulations were telling astronomers what to look for before the observational surveys were sophisticated enough to confirm it. When the confirmation came, as increasingly detailed maps of the galaxy distribution were assembled, it was, in a scientific sense, satisfying rather than surprising. The web was there because the physics predicted it would be, and the physics turned out to be right. But there's something worth sitting with here that goes beyond the scientific satisfaction of a prediction confirmed. The structure of the largest thing in the universe was built into physics from the very beginning. It wasn't a coincidence or a local accident or something that happened to develop this way in our region of the cosmos. It was a consequence playing out across billions of years of conditions that existed in the first fraction of a second after the universe began. The cosmic web is, in a sense, the shape that the laws of physics take when given enough time and enough space to fully express themselves. The universe has a structure, and that structure was determined almost at the very beginning. The filaments are not static, they're not permanent features of a fixed cosmic landscape. They evolve. In the early universe, before galaxies formed, when the universe was much smaller, much denser, and full of hot gas rather than stars, the pattern of dark matter was already beginning to emerge. Tiny fluctuations in density, present since the very beginning, began to be amplified by gravity. Regions that were slightly denser than average attracted more matter toward them. Regions that were slightly less dense than average lost matter to their denser neighbors. Over hundreds of millions of years, these small initial differences grew. The slightly denser regions became filaments. The slightly less dense regions became voids. Galaxies formed preferentially in the denser regions because that's where the gas was most concentrated, most likely to collapse under gravity and form stars. And the web that resulted, the structure of filaments and voids, Tego is the grown-up version of those tiny, the small differences from the very beginning of the universe, expanded and amplified over 13.8 billion years into the largest structures that have ever existed. The cosmic web is, in the most literal sense, a relic, a direct descendant, transformed almost beyond recognition, but continues in every physical way of the conditions that existed at the very beginning of everything. The voids, where almost nothing lives. If the filaments are the threads of the cosmic web, the voids are the spaces between them. And the voids deserve as much attention as the filaments because in their own way, they're just as extraordinary. A void, in the context of the cosmic web, is a region of space that is nearly not completely, but nearly devoid of galaxies. The matter that might have formed galaxies there was drawn away over billions of years to the denser filaments surrounding the void, leaving behind a vast, empty sphere of space. Some voids are relatively modest, tens of millions of light years across. Others are enormous. The largest confirmed void in the observable universe is hundreds of millions of light years in diameter. Hundreds of millions of light years of almost nothing. To understand what almost nothing means in this context, consider what ordinary outer space, the space between the stars in our galaxy, is like. It's not completely empty. It contains gas, extremely thin gas, far too thin to breathe, far too thin to detect without sensitive instruments at densities of roughly 1 atom per cubic centimeter. 1 atom, on average, in every cube of space the size of a sugar cube. That's what we mean when we say outer space is almost empty. Now consider the interior of a cosmic void. The density of matter in the deep interior of a large void can be 10 to 20 times lower than the average density of the universe. The average density of the universe is already extraordinarily low, far lower than the best vacuum we can create in a laboratory on Earth. And a void is 10 to 20 times lower than that. It is, in any practical sense, as close to nothing as anything in the physical universe comes. And yet voids are not quite empty. Even in the deepest, emptiest regions, a small number of galaxies exist. Not many, not the dense populations found along filaments, but some small, isolated, faint galaxies adrift in an enormous emptiness, separated from the nearest other galaxy by distances so large that the sky above any planet in such a galaxy would look different from our own. Fewer bright galaxies visible, more of the sky simply dark. These void galaxies are among the most isolated objects in the universe. They formed there in the low-density environment of the void early in cosmic history, and have since been drifting the void, expanding around them as the universe expands, pushing them further and further from everything else. There are galaxies in the universe that have been essentially alone for billions of years, surrounded by emptiness in every direction for distances that make solitude, in any human sense, seem like a crowded concept. The voids are not just empty space, they're active participants in the structure of the cosmic web. As the universe expands, and it is expanding continuously, the space between galaxies and between filaments growing as time passes, the voids expand with it. The matter on the edges of the void is attracted by the denser filaments surrounding it and slowly drains away, making the void ever more empty at its center and feeding the filaments at its edges. The voids are, in a sense, clearing themselves, becoming more void over time as their matter migrates toward the web surrounding them. And this means the structure of the cosmic web is not in equilibrium. It's not a stable architecture that has reached its final form and will remain this way. It's a dynamic system, continuously evolving, the voids growing, the filaments becoming denser, the nodes at their intersections accumulating more and more mass over time. The cosmic web we observe today is not what the cosmic web looked like 10 billion years ago, and not what it will look like 10 billion years from now. It's a moment, a snapshot, a particular configuration of the universe at this specific point in its history. And we happen to exist at this moment, at this configuration, in this particular web. Galaxy clusters, the knots of the web, where filaments intersect, where two or more threads of the cosmic web meet the concentration of matter is highest. And in these regions, the largest gravitationally bound structures in the universe have formed galaxy clusters. A galaxy cluster is not just a group of galaxies in the same general region of space. It's a gravitationally bound system, a structure held together by gravity, within which individual galaxies move the way stars move within a galaxy, bound to each other by the mutual gravitational attraction of the entire system. The largest galaxy clusters contain thousands of galaxies, not hundreds, thousands. Each galaxy with hundreds of billions of stars. The total mass of a large galaxy cluster is enormous, 1,000 trillion times the mass of the Sun in some cases. And most of that mass is not in the galaxies. It's in hot gas that fills the space between the galaxies. Gas so hot that it glows in X-ray light, detectable by space-based telescopes sensitive to high-energy radiation. And most of the mass overall is in dark matter, the invisible scaffolding that holds the whole structure together. Clusters are the knots of the web, the places where filaments terminate, where matter has been accumulating for billions of years, drawn in from the surrounding region by the immense gravity of everything that had already gathered there. And they're still accumulating, still growing, still drawing matter from the filaments that feed into them. The clusters we observe today are not finished objects. They're works in progress, structures that have been growing for most of the age of the universe and will continue growing for billions of years to come as the universe delivers more and more material to these concentration points through the filamentary threads of the web. The largest known structures in the universe are not individual galaxy clusters. They're associations of clusters, what are called superclusters, or at the largest scales, complex structures that span hundreds of millions of light years and encompass dozens or hundreds of individual clusters, all connected by filaments. Our own galaxy sits within one of these. The Milky Way is a member of a small group of galaxies, the local group containing a few dozen galaxies, the largest of which are our own and the Andromeda galaxy. This local group sits near the edge of a larger structure called the Virgo supercluster, which itself sits at the edge of an even larger structure, an enormous supercluster complex that astronomers have mapped in increasing detail over the past few decades. When this larger structure was properly mapped and its full extent recognized, it was given a name, Laniakea, from the Hawaiian, meaning immeasurable heaven. Laniakea is a supercluster complex roughly 500 million light years across, containing about 100,000 galaxies, and with a total mass of roughly 100 million billion times the mass of the Sunday, the Milky Way, our galaxy, with all its hundreds of billions of stars, all its ancient history, all its planets, is a small member of a small group near the edge of this enormous structure. We are in the suburbs of Laniakea, which is itself a modest-sized node in the cosmic web, our place in the web, a small address in a very large structure. There's a particular kind of humility that comes from understanding your location in the cosmic web. Not a discouraging humility, not the kind that makes things feel meaningless. More like the kind that comes from standing somewhere very high and understanding for the first time how large the landscape actually is. The Milky Way is a large galaxy by some measures. It contains several hundred billion stars. It's been forming stars for most of the age of the universe. It has a history written in the ages and compositions of its stars that stretches back almost to the beginning of everything. And in the context of Laniakea, it's small. Laniakea is in the context of the cosmic web as a whole, one node among countless others stretched across hundreds of millions of light years of filamentary structure. And the cosmic web encompasses the entire observable universe, approximately 93 billion light years across, containing approximately 2 trillion galaxies, all organized into this filamentary architecture. Our address in this structure, if you tried to write it out completely, would go something like this: Planet Earth, Solar System, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea supercluster complex, a filament of the cosmic web, the observable universe. Each level of this address contains billions of objects at the level below it. And the whole thing, every galaxy, every star, every planet, every molecule, every atom, every piece of matter or energy of any kind is embedded in the same cosmic web. Everything is connected to everything else through this structure. Not directly, not instantly, the universe is too large for that, but through the web, through the filaments that connect clusters to clusters and the clusters to each other in a single, continuous, universal architecture. There's something I want to sit with here before we move on. The cosmic web is not just a scientific concept. It's a fact about the nature of the universe, about what the universe actually is at its largest scales. And one of the things that fact implies is that isolation in any cosmic sense is not really possible. The Milky Way is not alone in empty space. It's embedded in a web of matter, dark matter mostly, but also gas, and eventually the light and influence of billions of other galaxies that connects it through a chain of gravitational interactions to every other major structure in the observable universe. The distance is too large for that connection to be practically meaningful in any immediate way. The timescales involved dwarf anything in human experience. But in a physical sense, in the sense of being part of a continuous structure shaped by the same forces, embedded in the same architecture, nothing in the observable universe is truly alone. Every galaxy is part of the web. Every star is inside a galaxy that is part of the web. Every planet, every person, every thought being had right now, all of it is inside a star system that is inside a galaxy that is inside the cosmic web. The web and time, how the architecture has changed. I want to go back to the beginning, not of the story, but of the universe itself. Because the cosmic web, as we see it now, is not what it has always looked like. It's the product of billions of years of evolution, starting from conditions so different from the present that they barely seem connected. In the first moments after the beginning of the universe, in the first fraction of a second, everything was compressed into an unimaginably hot, dense state. There were no galaxies, no stars, no atoms even, just a plasma of fundamental particles at temperatures so extreme that the matter and energy we're familiar with couldn't exist. The universe expanded, cooled. After a few minutes, protons and neutrons combined into nuclei. After about 380,000 years, the universe had cooled enough for electrons to combine with nuclei, forming atoms for the first time and releasing the light that we still detect today as the cosmic microwave background. The faint glow of the ancient universe, still present everywhere in space, in every direction, but there were no structures yet, no galaxies, no stars, just an almost perfectly uniform sea of gas, mostly hydrogen and helium, filling the entire universe, expanding slowly outward, almost perfectly uniform, but not quite. There were tiny differences in density from place to place, fluctuations so small that they had to be measured by the most sensitive instruments ever built, differences of only about 1 part in 100,000. 1 part in 100,000. And those tiny fluctuations, those almost imperceptibly small variations in the density of the early universe are the seeds from which the entire cosmic web grew. Under the influence of gravity, the slightly denser regions attracted more matter, not quickly, incredibly slowly, by any human standard. But over hundreds of millions of years, the differences grew. The denser regions became more dense. The less dense regions became less dense as matter drained toward the attractors. The cosmic gas, initially almost uniform, began to develop structure. The first structures to form were the dark matter halos, concentrations of dark matter, roughly spherical, in which ordinary matter gathered and eventually collapsed into the first stars and galaxies. These first galaxies formed roughly a few 100 million years after the beginning. Small, irregular, very different from the large, structured galaxies we see in the universe today, but real. And already, even at this early stage, the web was beginning to emerge. These early galaxies were not randomly distributed. They were forming preferentially along the dark matter filaments that were themselves growing from the same initial fluctuations. Over the next several billion years, the web developed. Filaments grew longer and denser. Voids expanded and emptied. Clusters accumulated at the intersections of filaments. Galaxies merged and grew, some becoming the enormous elliptical galaxies we see at the centers of today's largest clusters. The cosmic web we observe today, the one that has been mapped by galaxy surveys covering billions of light years, is the result of almost 14 billion years of this process. 14 billion years of gravity, working patiently on those initial 1 in 100,000 density fluctuations, building up from almost nothing to the largest structures in the universe. The web is old, almost as old as the universe itself, and it's still growing. What the web tells us, reading the universe's history in its structure, there's a reason cosmologists study the cosmic web so carefully beyond the immediate fascination of understanding what the universe looks like. The structure of the web contains information encoded in the pattern of filaments and voids and clusters, is a record of the history of the universe, of how it began, how it evolved, what it's made of, and in what direction it's heading. The specific pattern of the web, the sizes of the voids, the lengths and thicknesses of the filaments, the masses and distributions of galaxy clusters is sensitive to the physics of the early universe and to the properties of its components. In particular, it's sensitive to the properties of dark matter and dark energy, different assumptions about dark matter, its amount, its properties, how it interacts gravitationally, produce different predictions for the large-scale structure. So, do different assumptions about dark energy, the mysterious component that makes up roughly 68% of the universe's energy content and is responsible for the accelerating expansion of space. By comparing the observed large-scale structure of the universe with predictions from computer simulations that incorporate different assumptions about these components, cosmologists can constrain what those components must be like. The web is, in this sense, a diagnostic tool, a way of probing the fundamental nature of the universe's dominant components by looking at the imprint they've left on the largest scales. This is one of the reasons the large surveys of galaxy distribution surveys that have mapped hundreds of millions of galaxies across billions of light years are so scientifically valuable. They're not just maps, they're measurements. Measurements of the history and composition of the universe, written in the positions of galaxies. There's something almost philosophical about this idea. The universe has been running continuously for almost 14 billion years. In that time, it has done something extraordinary. It has built its own history into its structure. The web we observe today is not just the description of where things are now. It's a record of where they were and how they got there and what they were made of and what forces acted on them. The universe, in a sense, is its own archive. And we, with our telescopes and our surveys and our computer simulations, are learning to read it. Not completely, not yet. There are aspects of the cosmic web that remain poorly understood. The properties of dark matter and dark energy remain unknown in a fundamental sense, even though their effects are measurable. The details of how galaxies form and evolve within the web are still actively researched. The full three-dimensional map of the web, extending to the edge of the observable universe, will take decades more of work to assemble. But we're reading it slowly, carefully, with increasing precision, and what we're reading tells us that the universe is old and large and structured in ways that were determined almost at the very beginning, and that the structure itself encodes the answers to some of the deepest questions we can ask. The philosophy of connection, what it means to be part of something this large. I want to spend some time here near the end of tonight on something that isn't strictly scientific. Because I think the cosmic web, once you really understand what it is, raises questions that go beyond physics. Questions about meaning, about connection, about what it means to be a small thing inside a very large structure. These are not questions with scientific answers, but they're worth asking. The cosmic web connects everything, not in a mystical sense, not in any sense that defies physics or requires anything beyond the ordinary operation of gravity and the expansion of space. But in a genuine physical sense, everything in the observable universe is part of the same continuous structure, embedded in the same filamentary network, shaped by the same forces that have been operating since the beginning. The atoms in your body were made in stars that were themselves part of the cosmic web, embedded in filaments, orbiting within galaxies that were shaped by the dark matter structure of the web. Those atoms were scattered when the stars ended, drifted through interstellar space, were gathered into new clouds, eventually found their way into the solar system and the Earth, and ultimately into you. The path from the early universe to your hand is continuous. There's no point at which matter simply appears unconnected to what came before. The atoms in you have been part of the universe in various forms for as long as the universe has existed. And the universe has been shaped from almost the very beginning by the cosmic web, which means that in a very real, very physical sense, you are part of the web, not metaphorically, as a collection of atoms that were shaped by the same large-scale structure that shapes everything else, that were part of stars, that were part of galaxies, that are part of the web. There's a word for this kind of connection, though it's usually used in other contexts. Continuity. The cosmic web represents a continuity of structure, from the tiny fluctuations in the early universe to the filaments and clusters and superclusters of today. The atoms in your hand represent the continuity of matter, from the nucleosynthesis in ancient stars to the cells of a living body. Nothing was created from nothing. Nothing appeared in isolation. Everything that exists is the current state of something that has been changing continuously since the beginning. I find something steadying in that, not because it answers the deep questions about meaning or purpose, it doesn't, but because it places things in a context in which isolation is, at a fundamental level, not quite real, in which every object, every particle, every arrangement of matter is connected through time and through the web to everything else. The cosmic web is also, I think, one of the most powerful reminders that the universe is not human-scaled. This might seem obvious. Of course, the universe is not human-scaled, it's enormous. We've always known it was enormous. But the cosmic web makes the enormousness specific in a way that's different from just citing large numbers. It gives the enormousness a shape, a structure. It shows that the universe is not just large in an abstract numerical sense, but large in a way that has produced things, superclusters, filaments, voids for which human language has barely adequate words, because human language evolved to describe things at human scales. The largest structure in the observable universe is something like the Hercules Corona Borealis Great Wall, a filamentary structure roughly 10 billion light years across. 10 billion light years. Light has been traveling for 10 billion years and has not crossed this structure from one side to the other. And this is one structure in a universe full of structures. The universe does not fit in the human mind, not completely, not with full intuitive comprehension. And I think that's all right. I think there's something appropriate about a universe that exceeds our comprehension, something that in its own way reflects the scale of what's here, the genuine, physical, almost overwhelming scale of the reality we're embedded in. We don't need to fully comprehend it to be part of it. We already are part of it. We've always been the future of the web, where everything is going. I want to end the scientific part of tonight with a look forward, not at what the cosmic web is now, but at what it will become. The universe is expanding. This is one of the most well-established facts in modern cosmology, not just expanding, but expanding at an accelerating rate, driven by dark energy, the mysterious component that makes up most of the universe's energy content. This accelerating expansion has consequences for the cosmic web. In the near term, which in cosmological terms means the next few billion years, the expansion doesn't dramatically change the web structure. The web will continue to evolve as it has been evolving. Voids expanding, filaments feeding clusters, clusters growing. The web will become more pronounced, more structured, as the density contrasts between the filaments and the voids increase. But on longer timescales, the accelerating expansion begins to work against the web. Eventually, far in the future, billions upon billions of years from now, the expansion of space will be moving the distant parts of the universe away from each other faster than gravity can hold them together. Galaxy clusters, which are gravitationally bound and will survive, will become islands. The filaments that now connect the clusters will thin and fade. The voids will grow until they encompass most of the observable universe, except that what's observable will itself be shrinking as the accelerating expansion pushes distant galaxies beyond the cosmic horizon, where their light can no longer reach us. In the very far future, if any civilization exists in the remnant of the Milky Way and its surrounding cluster now merged into a single large galaxy, they will look out into space and see almost nothing. A few nearby galaxies, the remnants of what was once the local group, and beyond that, darkness. The evidence that there was ever a cosmic web, the light from distant galaxies, the patterns in the distribution of matter will have expanded beyond reach. A future civilization, starting from scratch, with only what's locally observable, would have almost no way of knowing the universe was ever as large as it is, almost no way of knowing the cosmic web existed. We live in a privileged moment, a moment when the web is visible, when the distant universe is reachable by light, when the full architecture of everything can, in principle, be observed and understood. This window will not remain open forever. Before we continue tonight, I want to ask you something the way I always do. Tell me where you're listening from, what country, what city, if you'd like to share. And tell me what time it is for you right now, because somewhere as you hear these words, it is very late, and the house around you has gone completely quiet, and the only sound is the soft, slow rhythm of your own breathing, and perhaps this voice moving gently through the dark toward you. Somewhere else, it is just past midnight. And somewhere, it may be almost morning, the sky outside the window beginning to lighten at its very edge, the dark becoming something almost blue, I like knowing that I like holding the image of all of you scattered across so many rooms, so many different kinds of nights, each arriving in your own way at the same place, ready finally to set the day down. Tonight, we finished something. We started in the first part of this journey. We traveled very far. We looked at your hand and at the star material inside it. We built the picture of the universe's largest structure, slowly and carefully starting from the room you're in, expanding outward, step by step, until we arrived at something that may be the largest single idea the human mind can attempt to hold, the cosmic web. We learned what it is, a vast filamentary network of dark matter and ordinary matter stretching across the entire observable universe, organizing every galaxy, every cluster, every supercluster into a single continuous architecture. We learned where it came from tiny fluctuations in the density of the very early universe, amplified by gravity over nearly 14 billion years into the largest structures that have ever existed. We learned about the filaments, the nodes, the voids, and the invisible architect dark matter that built and maintains the scaffolding of everything. We ended at the future, the sobering picture of what accelerating expansion will eventually do to the web, slowly dissolving it into isolated islands, erasing the evidence of its existence from the observable sky. Tonight, we go further still. We're going to spend time with what the cosmic web means, not just as a scientific fact, but as a feature of reality that changes how you might think about yourself, about connection, about your place in the largest structure that has ever existed. We're going to look at some of the most extraordinary specific features of the web, the structures within it that push language to its limits, the phenomena that happen along its filaments, the strange and beautiful things that become possible only at these scales. And then, at the end, we're going to do what we always do, come all the way back to this room, back to this night, back to you, and what all of this might mean for something as small and specific and real as a single human life. So get comfortable, let your weight settle, let your breathing slow a little, and let's go back out there to the largest place there is. Section 2, the scale problem, revisited. We mentioned in the first part that there's a particular problem with trying to describe the cosmic web, the problem of scale, the fact that the human mind evolved to understand things at a certain range of sizes, and that the cosmic web exceeds that range so dramatically that even our best mathematical tools feel in some ways inadequate. I want to spend a little more time with this problem tonight, not to resolve it, because it can't really be resolved, but because I think sitting with it carefully is one of the more honest things we can do when thinking about the universe at its largest scales. Consider what it means to truly understand something, as opposed to merely knowing a fact about it. When I say this room is about 5 meters across, you don't just know that as an abstract fact. You feel it, you can walk it, you can gesture to indicate the walls. Your body has an intuition for 5 meters, a felt sense of the distance, because you've spent your life moving through spaces of roughly that size. When I say the Milky Way is 100,000 light years across, something different happens. You can know that as a fact. You can perform mathematical operations with the number, but you don't feel it. Your body has no intuition for 100,000 light years, because no human body has ever experienced anything at that scale. The number is real and the distance is real, but your felt relationship to it is essentially nothing. And the cosmic web is thousands of times larger than the Milky Way. This isn't a failure of intelligence. It's a structural feature of the kind of mind that evolution produced. Our minds are extraordinarily good at the scales that matter for survival distances of meters to kilometers, timescales of seconds to decades. Beyond those ranges, we can operate mathematically, but we can't feel. I think acknowledging this honestly actually makes the cosmic web more interesting, not less, because it means that what we're attempting when we try to understand the web is something genuinely unprecedented in the history of minds, an attempt by a small, evolved creature to comprehend something that is, in every sense, beyond its native comprehension. And the fact that we can do it at all imperfectly, approximately, through the tools of mathematics and simulation and analogy is itself remarkable. We can know things we cannot feel. We can understand structures that no mind could ever directly experience. We can, through the accumulated effort of science across centuries, access a picture of reality that is radically larger and stranger than anything our intuitions alone could ever access. That is an extraordinary thing about minds like ours. Section 3, the web in numbers. I want to give you some numbers now, not to overwhelm, but to anchor, to give you specific, real, verifiable figures that can serve as reference points as we continue building the picture. The observable universe is approximately 93 billion light years across. This is the region from which light has had time to reach us since the beginning of the universe. It contains approximately 2 trillion galaxies. 2 trillion. Written out, 2 followed by 12 zeros. 2,000 billion. If you counted one galaxy per second without stopping, it would take over 63,000 years to count them all. Each of these galaxies contains, on average, hundreds of billions of stars. The Milky Way is on the larger side, with several hundred billion. Smaller galaxies might have tens of millions. Larger ones, the giant elliptical galaxies that sit at the centers of the largest clusters, might have trillions. The total number of stars in the observable universe is estimated at somewhere around 1 to 2 times 10 to the power of 24. That's a 1 or 2 followed by 24 zeros. A number so large that it genuinely defies any attempt at intuitive comprehension. Now, the cosmic web, the largest confirmed structure in the observable universe, as of our current knowledge, is the Hercules Corona Borealis Great Wall, a filamentary structure roughly 10 billion light years in its longest dimension. 10 billion light years. Light traveling at the maximum speed allowed by physics would take 10 billion years to cross this structure from one end to the other. For comparison, the universe is 13.8 billion years old. Light set off from one end of this structure before the solar system existed and has not yet reached the other end. The Laniakea supercluster, our own cosmic neighborhood at the supercluster scale, is roughly 500 million light years across, contains about 100,000 galaxies, and has a total mass equivalent to roughly 100 million billion times the mass of our Sunday, the Sloan Great Wall, one of the first truly enormous structures to be mapped in detail, stretches approximately 1.4 billion light years. Individual cosmic voids, the empty regions between the filaments, range from roughly 30 million light years across for smaller voids, up to hundreds of millions of light years for the largest. The Boötes void, one of the most famous, is roughly 300 million light years in diameter. It was discovered when astronomers conducting a survey of galaxies found a region that, by all expectations, should have contained around 2,000 galaxies and contained instead fewer than 60. 300 million light years. Almost empty. These are the numbers. Real, verified, extraordinary. Section 4. What dark matter actually is and isn't. I want to spend some time tonight on dark matter, not just as the invisible architect of the cosmic web, which we established in the first part, but as one of the deepest and most honest mysteries in all of science. Because I think the honest story of dark matter is more interesting than the simplified version, and it's worth telling carefully. Dark matter is a name for something we don't understand. That sounds more dismissive than I mean it. Let me be more precise. Dark matter is a name for whatever is causing the observed effects that ordinary matter cannot account for. Those effects are real. They're well measured. They're consistent across many different types of observation, made by different groups using different methods in different parts of the sky. Galaxies rotate at speeds that would, if their mass were only the visible stars and gas, cause the outer parts of the galaxy to fly apart. They don't fly apart. Something additional is holding them together. Whatever that something is, we call it dark matter. Light from distant galaxies is bent by the gravity of clusters in front of them, a phenomenon called gravitational lensing, predicted by general relativity. The degree of bending corresponds to a certain amount of mass. The mass inferred from lensing is consistently much larger than the mass of visible matter in the cluster. Something additional is contributing the extra gravity. Whatever that something is, we call it dark matter. The cosmic web, the pattern of filaments and voids that we observe in the distribution of galaxies, matches the predictions of computer simulations that include dark matter and does not match the predictions of simulations that omit it. Something is providing the scaffolding on which the web is built. Whatever that something is, we call it dark matter. What dark matter actually is at the particle physics level, what kind of particle or particles or fields or whatever category of thing it might be, we genuinely don't know. We have hypotheses. Some of the best motivated hypotheses come from extensions of the standard model of particle physics, hypothetical particles called WIMPs, weakly interacting massive particles, that would have the right properties to account for dark matter's effects. Other hypotheses suggest different kinds of particles, or even modified theories of gravity that might explain the observations without requiring any new form of matter. Experiments designed to detect dark matter particles, directly extraordinarily sensitive detectors placed deep underground to shield them from background radiation, waiting for the rare event of a dark matter particle interacting with ordinary matter, have been running for years and have not produced a confirmed detection. This doesn't mean dark matter doesn't exist. It means that either dark matter is not the kind of particle those experiments are designed to detect, or the experiments haven't yet reached the required sensitivity, or there's something we're not yet understanding correctly. The honest scientific position is something is causing these effects. We call it dark matter. We don't know what it is. And this is one of the most important open questions in physics today. Answering it, discovering what dark matter actually is, would be one of the most significant scientific discoveries in human history. Tonight, as you lie here and the darkness around you is full of whatever's in it, the darkness of the universe is full of something we don't understand that outweighs everything we can see by a factor of roughly 5 to 1. The universe is mostly dark, mostly unknown, and the largest structure in it is built primarily from that dark unknown. Section 5. Dark energy and the expanding web. Dark matter is one mystery. Dark energy is another, and in some ways an even stranger one. The universe is expanding. This has been known since the 1920s, when observations of distant galaxies showed that they were moving away from us, not because they're moving through space in the ordinary sense, but because space itself is expanding, carrying the galaxies along with it the way dots drawn on an inflating balloon move apart as the balloon expands. For much of the 20th century, the expectation was that this expansion would be slowing down. Gravity after all, is attractive. Everything pulls on everything else, and the cumulative gravitational attraction of all the matter in the universe should, over time, be working against the expansion, decelerating it. In 1998, two independent teams of astronomers, both studying the brightness of distant supernovae, which can be used as distance indicators, found something they didn't expect. The expansion of the universe is not slowing down, it's speeding up. This was genuinely shocking. It meant that whatever is causing the expansion to accelerate, whatever is providing the energy to push space apart against gravity, is something that was not accounted for in the existing understanding of the universe. This unknown something was named dark energy, and we know even less about it than we know about dark matter. Dark energy makes up approximately 68% of the universe's total energy content. It is the dominant component of the universe. It determines the ultimate fate of everything, and we don't know what it is. We know some things about what it does. It has the effect of a repulsive force, not a force in the classical Newtonian sense, but an effect of the energy content of space itself, causing space to expand at an accelerating rate. The observational evidence for this acceleration is now extremely strong. It has been confirmed by many different methods and is one of the most robust results in modern cosmology. The leading theoretical candidate for dark energy is something called the cosmological constant, an energy of empty space, first introduced by Einstein for different reasons, and later retracted, and now observationally motivated. But the value of the cosmological constant that would account for the observed acceleration of expansion is, when compared to theoretical predictions from quantum field theory, discrepant by a factor that is one of the largest mismatches between theory and observation in the history of physics. Other possibilities have been proposed: a dynamic field, sometimes called quintessence, whose energy density changes over time, modifications to general relativity at cosmic scales, other more exotic ideas. None has been definitively confirmed. Dark energy is the dominant component of the universe. It is reshaping the cosmic web on the longest timescales. It will determine the ultimate fate of every galaxy, every star, every structure in existence. And we don't know what it is. The universe is full of things we don't understand. And I think there is something important in sitting with that. Honestly, not as a source of frustration, but as a reminder of how early we are in this project of understanding. We have learned an extraordinary amount in the past century. We have mapped the large-scale structure of the universe, discovered the expansion and its acceleration, identified the presence of dark matter and dark energy, traced the history of the universe back to its earliest moments. And we are still, by any honest measure, in the early chapters. Section 6. The filaments up close. Let me take you inside a filament, not metaphorically as close to literally as words can manage. Let me try to describe what it would be like, what you would encounter, what you would see, what the environment would be like if you could somehow navigate along one of the great filaments of the cosmic web. You are in intergalactic space. You are not near any galaxy. You are in the space between galaxies, inside the filament, but between its concentration points. The first thing you would notice, if you could somehow perceive it directly, is that the space around you is not quite empty. It is filled with gas, extremely tenuous gas, far thinner than anything we could call a vacuum on Earth, but present nonetheless. This gas, called the warm-hot intergalactic medium, or WIM, is thought to contain a significant fraction of all the ordinary matter in the universe. Matter that has been heated as it fell into the gravitational potential of the filament to temperatures of hundreds of thousands to tens of millions of degrees. This hot gas in the filaments is nearly invisible. It doesn't emit light in the wavelengths that ordinary telescopes can see. It emits in X-rays and in certain specific signatures in the ultraviolet. Detecting it has been one of the major observational challenges of the past decades, and evidence for its existence has been accumulating, though mapping it fully remains an ongoing effort. Around you, at vast distances, galaxies are moving, not stationary moving. They're falling in slow motion by cosmic standards along the filament, drawn toward the massive clusters at the filament's ends. The galaxies are not evenly spaced along the filament. They cluster in some regions and are absent in others, creating a beaded appearance when seen from far enough away, the cosmic beads on a string structure that appears in simulations and is beginning to be confirmed by observations. The dark matter that provides the filament's gravitational backbone is everywhere around you, invisible, undetectable, except through its gravitational effects, but present in concentrations far higher than in the voids beyond the filament's edge. If you could travel along the filament, moving at some significant fraction of the speed of light, it would still take hundreds of millions of years to reach the cluster at the filament's end. The filament is not a thread in any human-scale sense. It is a structure so vast that the light travel time across it is comparable to the time our species has been fully anatomically modern. At the end of the filament, the cluster, dense, hot, enormous, the node where the web's threads meet. This is the environment of the cosmic web from the inside. Not empty, not uniform, structured, dynamic, flowing in the slowest possible motion over time scales that dwarf anything in human experience toward the gravitational centers of the universe's large-scale structure. Section 7. The node's galaxy clusters from the inside. Let's go to a node, to one of the great galaxy clusters that mark the intersections of the web's filaments. Imagine arriving at the outskirts of a large galaxy cluster. The environment begins to change. The gas density increases, the number of galaxies visible in every direction increases. You're entering the sphere of influence of one of the universe's largest gravitationally bound structures. A large galaxy cluster, something like the Coma cluster or the Perseus cluster, both of which have been studied in great detail, is an extraordinary environment. The space between galaxies in a cluster is not empty. It's filled with extremely hot gas, much hotter than the gas in the filaments, heated to temperatures of tens of millions of degrees or more by the process of falling into the cluster's gravitational well. This gas glows in X-rays, and X-ray telescopes in space have mapped it in detail for many clusters, revealing turbulent, complex, beautiful structures, shock waves where gas streams collide, vast cavities blown by jets from supermassive black holes at the centers of galaxies, gentle sloshing motions as the cluster's gas responds to the gravitational disturbances of recent mergers. The galaxies in a cluster are not all the same. At the center, typically, sits the largest galaxy in the cluster, a giant elliptical galaxy, often called the brightest cluster galaxy, that has grown to its enormous size by consuming other galaxies through mergers across billions of years. These central galaxies can be among the largest objects in the universe, containing trillions of stars stretching hundreds of thousands of light years across. The central galaxy typically hosts, at its very core, one of the largest supermassive black holes in the universe. Black holes, millions or billions of times the mass of the Sun, consuming material from the surrounding cluster and periodically erupting in jets of energy that can stretch for millions of light years, some of the most energetic events occurring in the universe today. Around the central galaxy, other cluster members, thousands of them, in a rich cluster orbit the gravitational center of the system. Some are large spiral galaxies like the Milky Way, still actively forming stars. Others are elliptical galaxies that have had their star formation suppressed, perhaps by interactions with the hot cluster gas or by previous mergers. Some are small, dwarf galaxies, barely visible against the background. The entire cluster is itself moving, falling slowly through the cosmic web toward other clusters with which it will eventually merge. Clusters grow by merging with other clusters in collisions so gradual that they take billions of years to complete, but so energetic that they release more energy than almost any other events in the universe. This is the node of the cosmic web: rich, complex, dynamic, energetic. The place where the universe's matter is most concentrated. The place where the web's threads end and where the largest structures in the universe spend their lives growing by consuming one another. Section 8. Galaxy formation and the web. The cosmic web is not just the backdrop against which galaxies exist. It is the environment that shaped galaxies that determines, to a very significant extent, what galaxies look like, how they evolve, and what kinds of stars and eventually what kinds of worlds they can produce. A galaxy forming in the dense environment of a filament close to a massive cluster experiences a very different life from a galaxy forming in the relative isolation of a void. Galaxies in dense environments and clusters at the intersections of filaments are subject to a range of processes that galaxies in isolation are not. The hot gas that fills clusters can strip the gas out of infalling galaxies, a process called ram pressure stripping, removing the raw material from which new stars would otherwise form, and quenching star formation in a way that transforms what might have been a blue star-forming spiral into a red star formation dead elliptical over cosmological timescales. Cluster galaxies also experience more frequent gravitational interactions with other galaxies, encounters that can distort shapes, trigger starbursts, or, when close enough, lead to full mergers. The largest elliptical galaxies we see today, including the giant central galaxies at the hearts of the biggest clusters, are the products of multiple such mergers, accumulated over billions of years. Galaxies in void environments, by contrast, are generally more isolated. They have more access to the cold gas that flows along filaments and feeds star formation. They tend to be more actively star-forming, more disk-like, more similar to the Milky Way's form. The Milky Way itself sits in a relatively modest environment, a small group of galaxies near the edge of a supercluster, in a region of the cosmic web that is not particularly dense by the standards of major clusters. This has allowed it to avoid the quenching effects that have transformed cluster galaxies to continue forming stars and to develop the disk structure and the relatively quiet environment in which eventually a solar system and a planet like Earth could form in a very real sense. The fact that you exist, the fact that Earth is a rocky, water-bearing planet orbiting a stable, middle-aged star in a star-forming galaxy is partly a consequence of where in the cosmic web the Milky Way happens to be. The web shaped the galaxy shaped the solar system shaped the planet shaped the conditions for life, and life over billions of years shaped you. The thread from the cosmic web to a human being lying in the dark listening to a story is not a metaphor. It is a physical chain of causation, real at every link. Section 9. Light and the web, what telescopes see. I want to spend some time on how we actually know what we know about the cosmic web, on the observational methods, the instruments the particular challenges and elegances of trying to map a structure of this scale, the most basic method is galaxy redshift surveys. When a galaxy moves away from us, which all sufficiently distant galaxies do, because of the expansion of space, the light it emits is stretched to longer wavelengths. This stretching shifts the wavelength of the light toward the red end of the spectrum, hence redshift. By measuring the redshift of a galaxy's light, we can determine how fast it's receding and from that, how far away it is. Galaxy redshift surveys, in which astronomers measure the redshifts of enormous numbers of galaxies, building up a three-dimensional map of their positions, have been among the most scientifically productive projects in modern cosmology. The Sloan Digital Sky Survey, which operated for years and covered roughly 1/3 of the sky, measured redshifts for hundreds of millions of objects. It revealed the large-scale structure of the universe in unprecedented detail: the filaments, the voids, the great walls of galaxies, the structure that we now identify as the cosmic web. The data from this survey has been used in thousands of scientific papers and continues to be mined for new insights. More recent surveys have pushed further to greater distances, more galaxies, wider areas of sky. The Dark Energy Spectroscopic Instrument, or DESI, is currently conducting a survey that will measure tens of millions of galaxy redshifts, building a map of the cosmic web across a larger volume than anything previously attempted. Beyond redshift surveys, other methods probe the web in complementary ways. Gravitational lensing, the bending of light from distant objects by the mass of intervening structures, can be used to map the distribution of matter, including dark matter, that redshift surveys cannot directly detect. By measuring subtle distortions in the shapes of millions of background galaxies, called weak gravitational lensing, astronomers can reconstruct maps of the matter distribution along the line of sight, including the dark matter that makes up most of the filaments. X-ray observations reveal the hot gas in galaxy clusters and in the more diffuse gas filling the filaments. The Chandra X-ray Observatory and the XMM Newton telescope have produced detailed maps of the hot cluster gas, revealing the complex physics of these enormous energetic environments. The Sunyaev-Zeldovich effect, a subtle distortion of the cosmic microwave background caused by hot electrons in galaxy clusters scattering the ancient light of the early universe, has been used to detect galaxy clusters, including clusters at distances so great that their light has been traveling for most of the age of the universe. And the cosmic microwave background itself, the faint, nearly uniform glow of the universe's earliest light, still filling all of space, still detectable by sensitive instruments, contains, encoded in its subtle temperature variations, the imprint of the density fluctuations that were the seeds of the cosmic web. Reading those fluctuations is like reading the initial conditions from which the web grew, the universe's own record of its beginning. Each of these methods reveals a different aspect of the same structure. Each illuminates a different component. Together, they build a picture of the web that is far richer and more detailed than any single method could provide. We are reading the universe's structure in every wavelength of light it emits, and what we're reading is the cosmic web. Section 10, Simulating the Universe, perhaps the most powerful tool for understanding the cosmic web, is not a telescope at all. It's a computer. Computer simulations of cosmic structure formation have been essential to our understanding of the web, both in predicting its existence before it was fully observed and in interpreting the observations we now have. The basic approach is this: start with the conditions of the early universe, the nearly uniform distribution of matter with its tiny density fluctuations, the proportions of dark matter, dark energy, and ordinary matter determined from observations, and apply the known laws of physics, allowing gravity and the other relevant forces to operate as they would in the real universe, stepping forward in time in small increments. The result, after billions of simulated years, should, if our understanding of the physics is correct, look like the universe we observe today. And it does, remarkably well. The largest cosmological simulations that have been run, simulations like the Millennium Simulation, Illustris TNG, and Flamingo model enormous volumes of the universe, tracking billions of particles of dark matter and ordinary matter, incorporating the effects of star formation, supernova, explosions, black hole accretion, and a range of other physical processes. They produce virtual universes whose large-scale structure, the distribution of filaments, voids, clusters, and the overall pattern of the web matches what we observe in the real universe with impressive fidelity. This agreement between simulation and observation is itself significant. It means that our understanding of the fundamental physics, the laws of gravity, the proportions of dark matter and dark energy, the initial conditions of the universe is at least approximately correct. The fact that the simulation, starting from the observed initial conditions and applying known physics, ends up looking like the observed universe is a powerful validation of the framework. But simulations also reveal things that observations alone cannot. They allow us to see the internal structure of filaments and clusters in 3 dimensions. They allow us to trace the history of individual structures, to follow a galaxy cluster backward in time, watching it form and grow. They allow us to run the same simulation with different assumptions about dark matter or dark energy and see how the resulting structure changes, which in turn constrains what the real dark matter and dark energy can be. The simulations have also revealed features of the web that are still being searched for observationally: the warm, hot intergalactic medium in the filaments, the precise connectivity of the web's network, the detailed dynamics of how matter flows from voids through filaments to clusters. We are simulating the universe, running it on computers from near its beginning, applying what we know and seeing what emerges. And what emerges is a web that looks like the one we observe. That is an extraordinary achievement of human understanding. Section 11. The web as network. I want to take a different perspective on the cosmic web for a moment, not astronomical, but mathematical. The cosmic web is, among other things, a network, a system of nodes connected by edges embedded in 3-dimensional space. And networks as a mathematical structure have properties that can be studied and quantified, properties that reveal things about how information, matter, and energy flow through the system. Network science, the mathematical study of complex interconnected systems, has developed rapidly in recent decades, driven by applications ranging from the internet to social networks to biological systems. And some of the tools developed for these earthly applications turn out to be applicable with modifications to the cosmic web. Galaxy clusters are the nodes of the network. The filaments are the edges, the connections between nodes. The properties of this network, how many connections each node has, how the connection strengths are distributed, how quickly you can travel from any node to any other node through the network, can be measured and compared with predictions from theory. When cosmologists do this analysis, they find that the cosmic web has properties similar to those found in other complex networks: a degree distribution that follows certain patterns, a clustering structure that reflects the hierarchical way the web formed, a network topology that is neither completely random nor completely regular, but falls somewhere in between. This network perspective also reveals something interesting about the web's resilience. Some nodes, the most massive clusters, are connected to many filaments, others are connected to only a few. This asymmetry means that removing a random node from the network would typically not disrupt the overall connectivity much, because most nodes are not highly connected. But removing the most highly connected nodes, the largest clusters, which sit at the intersections of many filaments, would have a much larger effect. The cosmic web, like many natural networks, has a kind of structural robustness against random perturbations, but a vulnerability at its most central points. This network perspective doesn't tell us new physics necessarily, but it gives us a different vocabulary for describing and thinking about the web, one that connects it to a broader landscape of complex systems and that may, in the long run, reveal connections and principles that more traditional astronomical analysis would miss. The universe's largest structure, viewed from a certain angle, is a network like other networks. One of the oldest and largest, and its structure, it turns out, is not so different from the structure of many systems that exist at far smaller scales. Section 12. The Web and Life, a cosmic perspective. I want to ask a question that is genuinely uncertain in its answer. And that, I think, is one of the most interesting questions that the cosmic web raises. Could life exist only where it exists in the cosmic web? Is our position in the web not at a major node, not in the depths of a void, but somewhere along a modest filament, a prerequisite for the kind of planet and solar system and galaxy that life requires? The honest answer is that we don't know. We have one example of life on Earth, and so we cannot make statistical arguments about where in the web life is likely or unlikely to arise, but we can reason about the factors that seem to matter. Life, at least as we know it, requires complex chemistry. Complex chemistry requires heavy elements, elements heavier than hydrogen and helium, which are produced in stars and distributed when stars end their lives. The availability of heavy elements depends on the history of star formation in a galaxy. Galaxies in cluster environments in dense nodes of the web tend to have their star formation quenched early in cosmic history by the harsh cluster environment. Some of the galaxies at the centers of today's largest clusters stopped forming stars billions of years ago. If life requires planets formed from stellar debris, and if those planets are more likely to form around younger generations of stars, then the centers of large clusters might not be the most hospitable regions for life. On the other hand, galaxies in void environments far from any filament in the emptiest regions of the web may have lower metallicity, fewer heavy elements, and therefore be less well suited to the formation of complex, rocky planets. The Milky Way, in its position on the outskirts of the Laniakea supercluster, in a region of modest density, has continued forming stars for most of cosmic history, producing the heavy elements needed for rocky planets, continuing to do so now. It may be that the sweet spot for life in terms of cosmic web position is exactly where we are, not in the extremes of density or emptiness, but somewhere in the intermediate regions where the conditions for complex chemistry have had time and material to develop. This is speculation, and I want to be honest about that. But it's the kind of speculation that points toward real questions. Questions about whether life's distribution in the universe might itself be shaped by the structure of the cosmic web. The web doesn't just organize matter, it may organize the conditions for life. Section 13. The universe's largest structures. Let me take you on a brief tour of some of the largest specific structures that have been identified in the cosmic web, named features that push language and comprehension to their limits. The Sloan Great Wall was, when discovered in 2003 using data from the Sloan Digital Sky Survey, the largest known structure in the universe. A filamentary structure stretching approximately 1.4 billion light-years, it's a complex of galaxies, filaments, and clusters arranged in a sheet-like form spanning an enormous arc of the sky. 1.4 billion light-years. If you set off from one end at the speed of light, the moment the first complex animals appeared on Earth, you would still be traveling. The huge LQG, the huge large quasar group discovered in 2012, is a structure composed of 73 quasars spanning approximately 4 billion light-years at its widest. Quasars are extraordinarily luminous cores of distant galaxies, powered by supermassive black holes consuming matter at enormous rates, bright enough to be seen across most of the observable universe. This grouping of 73 of them, arranged in a coherent structure, challenged the cosmological principle, the assumption that the universe is at sufficiently large scales, homogeneous and isotropic. Whether it truly constitutes a coherent bound structure or is a chance alignment remains a subject of discussion. The Hercules Corona Borealis Great Wall, which we mentioned in the first part, stretches approximately 10 billion light-years. Discovered through the clustering of gamma-ray bursts, the most energetic explosions in the universe, detectable across essentially the entire observable universe. It represents a density enhancement at cosmological scales that, if confirmed as a coherent structure, would be the largest known structure in existence. Its existence at such scales also pushes against our theoretical expectations for how uniform the universe should be at large scales, another active area of research. The Shapley supercluster is the most massive supercluster in our local cosmic neighborhood, a concentration of galaxy clusters roughly 500 million light-years away, containing dozens of clusters and an enormous amount of mass. It exerts a gravitational pull on our local region of the universe that is detectable in the peculiar motions of galaxies, including our own, toward it. The Perseus-Pisces supercluster is one of the large-scale structures that defines our cosmic neighborhood, a filamentary concentration of clusters that stretches roughly 45 degrees across our sky, located several hundred million light-years away. These are not just names on a list. Each of them is a real physical structure, a concentration of matter at scales that beggar imagination, doing things, evolving, merging, radiating, growing right now. As you lie here listening, the universe is full of named things this large, and they're all part of the same web. Section 14, how the web filters light. Here's something I find quietly wonderful about the cosmic web. It filters the ancient light of the universe in ways that carry information, and learning to read those filters is one of the ongoing achievements of modern cosmology. The cosmic microwave background, the faint glow of the early universe filling all of space, emitted when the universe was only 380,000 years old, has been traveling through the universe ever since. And as it travels, it interacts with the structures it passes through. When this ancient light passes through a cluster of galaxies, the hot electrons in the cluster's gas scatter it slightly, changing its spectrum in a characteristic way, the Sunyaev-Zel'dovich effect we mentioned earlier. By looking for this distortion across the sky, astronomers can find galaxy clusters, even ones too far away to be detected otherwise, because the distortion is present regardless of the cluster's distance. When the ancient light passes through the gravitational potential of a large structure, a supercluster, or a great wall, it undergoes a subtle frequency shift. photons climbing out of the gravitational potential of a large structure on the way to us lose a tiny amount of energy. And this effect, called the integrated Sachs-Wolf effect, creates very faint temperature differences in the observed cosmic microwave background. These differences correspond to the locations of large-scale structures, the Webb's nodes and filaments, leaving imprints on the oldest light in the universe. When the light from distant galaxies or quasars passes through the intergalactic medium, the gas along the filaments between us and the source, it's absorbed at specific wavelengths by hydrogen in the intervening gas. This creates a pattern of absorption features in the spectrum of the distant source, the Lyman alpha forest, that carries information about the distribution of gas along the line of sight. Reading this forest of absorption features is one of the methods used to probe the distribution of matter in the filaments of the web. Light from distant sources is also bent by the gravity of intervening structures, gravitational lensing, which can magnify, distort, or even create multiple images of the same source. The pattern of this lensing encodes information about the distribution of matter between us and the source. Another way of reading the structure of the web from the light that passes through it. The cosmic web is not just something that light travels through, it writes itself into the light as the light passes through it. And we, with the right instruments and the right analytical tools, can read what the web has written. The universe is teaching us its own structure in the language of light. Section 15. The quiet revolution in cosmology. I want to take a step back and talk about what it means historically, culturally, philosophically, that we now know the cosmic web exists. 100 years ago, we didn't know galaxies existed as separate systems. What we now call galaxies were thought by many astronomers to be nebulae within the Milky Way. The debate over their nature was only definitively settled in the 1920s when Edwin Hubble measured the distance to the Andromeda galaxy and showed that it was far beyond the boundaries of our own. 70 years ago, we didn't have anything like a three-dimensional map of the universe beyond our immediate neighborhood. The idea of mapping the positions of hundreds of millions of galaxies in 3 dimensions was science fiction. 50 years ago, the large-scale structure of the universe, the web, was not an established fact. There were hints, preliminary suggestions, theoretical predictions, but the detailed 3-dimensional observational confirmation was still decades away. Today, we have maps of the cosmic web spanning billions of light years. We have computer simulations that reproduce its structure from first principles. We have identified specific named structures within it that are among the largest things that have ever existed. We understand in broad outline how it formed from the initial conditions of the early universe. This is a quiet revolution. It doesn't always feel like a revolution because it happened incrementally over decades through the patient work of many people using many methods. No single dramatic announcement, no moment of sudden revelation. Just accumulation data and analysis and simulation and comparison, slowly building a picture that no single human mind could have assembled alone across a time scale, no single human life spans. And the picture that emerged is something no previous human culture could have imagined. The existence of a structure larger than anything expressible in human-scaled language, filling the entire observable universe, built from matter we cannot see, organized according to laws that were written into the universe at its very beginning. We live in a time when this picture exists, when it's accessible imperfectly through analogy and metaphor and the mathematics. Most of us don't speak fluently, but accessible. When a person lying in the dark at night can hear about it and can, with some effort and some patience, begin to hold something of its shape in their mind. That is not a small thing. It may be one of the most remarkable things about the particular moment in history that we happen to live in. Section 16, the web and the self. Now I want to bring all of this back gradually, gently to something much smaller. To you, not in a way that diminishes the web or inflates the self, but in a way that honors the actual relationship between these two things, the largest structure in the universe and the small, temporary, remarkably complex arrangement of matter that is a single human being. The atoms in your body, as we established at the very beginning of the story, came from stars. Stars that lived and died before the solar system existed, that fused the hydrogen and helium of the early universe into heavier elements through billions of years of nuclear burning, and that scattered those elements when they ended. Those stars were part of the Milky Way. The Milky Way is part of the local group. The local group is part of Laniakea. Laniakea is a node in the cosmic web, which means that the material that became you, the atoms forged in those ancient stellar furnaces, scattered across interstellar space, eventually gathered into a molecular cloud, collapsed into a new solar system, distributed across a small rocky planet, and eventually, through billions of years of geological and biological evolution, organized into the extraordinarily complex structure of a living human being. That material has always been part of the web. It was part of the web when it was hydrogen gas in the early universe, slowly gathering under gravity along the first dark matter filaments. It was part of the web when it was inside the nuclear reactions of stars. It was part of the web as interstellar dust drifting through the Milky Way. And it is part of the web right now, organized into you lying here, listening. The web did not produce you in any direct or intentional sense. There is no pathway of efficient causation from filament to human. The connection is more fundamental, more about shared physical history, about being made of the same stuff, shaped by the same forces, embedded in the same structure. But the connection is real. And it is, if you let yourself feel it rather than just think it, genuinely remarkable. Section 17. What solitude means in a web. The cosmic web raises a question about solitude that I find worth exploring. We talk about loneliness sometimes as though it were primarily a social fact, a matter of whether other people are nearby, whether we feel connected to those around us. And in the most immediate, emotionally meaningful sense, that's right. The presence or absence of connection with other people is enormously significant to human beings, and the loneliness of feeling isolated from other minds is real and serious and deserves attention. But the cosmic web suggests a different way of thinking about isolation, one that operates at a completely different scale. At the scale of the cosmic web, nothing in the universe is truly isolated. Every structure is connected to every other structure through the filamentary network. The forces that operate at cosmic scales, gravity, the expansion of space, act everywhere, on everything, all the time. There is no piece of matter in the observable universe that is not, in some sense, in relationship with every other piece. This is not a claim that dissolves loneliness. The felt experience of social isolation cannot be resolved by pointing to cosmic connectivity. The human need for connection is real, and it operates at human scales, and it cannot be satisfied by knowing that the atoms in you are gravitationally connected to atoms in the Andromeda galaxy. But I think there's something worth sitting with here. Nonetheless, the sense of isolation, of being a small, separate, disconnected thing in an indifferent universe is, at a certain level of analysis, physically inaccurate. You are not separate from the universe. You are the universe temporarily organized into a form capable of asking whether it's separate from the universe. The atoms that make you are part of the same material that makes the filaments and the clusters and the voids and the great walls of the cosmic web. The forces that act on you, gravity, electromagnetism, the rest are the same forces that act on everything else, operating continuously, connecting everything in the physical sense. There is a kind of comfort available in that, I think, for those moments when the sense of isolation is most acute, not a resolution, not a substitute for human connection, but a perspective, a reminder that the feeling of being a separate, disconnected speck in an indifferent void is, at a certain level of analysis, based on an incomplete picture. The void is not indifferent. It's not even really a void. It's the web, and you're in it, like everything else. Section 18. The privilege of this moment. We mentioned at the end of the first part that the accelerating expansion of the universe will eventually dissolve. The cosmic web will push galaxies beyond each other's horizons, erase the evidence of large-scale structure from the observable sky, leave any future civilizations with almost no way of knowing the web existed. I want to spend a little more time with what this means. Right now, at this particular moment in cosmic history, 13.8 billion years after the beginning, the cosmic web is at a particular stage of its development. It has had enough time to develop clear, well-defined structure with filaments long enough to span hundreds of millions of light years and clusters massive enough to contain thousands of galaxies, but it has not yet been erased by the ongoing expansion. The distant galaxies are still within observational reach. The large-scale structure is still detectable. The web can be mapped. This window in which the web exists in a developed form and in which its evidence is accessible to observers within it is not permanent. On the timescales of cosmology, it may even be relatively brief. And within this window, in the tiny sliver of cosmic time that is the span of human civilization, we have developed the tools to see the web, to map it, to simulate it, to understand something of its nature. This is not something that was guaranteed. The universe could have been such that no life arose, or that life arose without the capacity for abstract thought, or that the capacity for abstract thought arose without the particular inclination towards systematic observation and theory that is science. There are countless ways in which the specific achievement of cosmological understanding of knowing roughly the shape of the universe at its largest scales could have not happened. But it did happen. In this particular window, on this particular planet, members of one particular species developed the understanding to see the cosmic web. We are the universe looking at itself at this particular level of scale, in this particular window of time. That seems worth sitting with. Section 19, the web and wonder. I want to say something about wonder, because I think it's the most honest response to what we've been discussing, and because I think it deserves to be named. Wonder is a particular kind of attention. It's what happens when something exceeds our existing categories for understanding it, when the thing in front of us is too large or too strange or too intricate to be immediately assimilated into what we already know. It's the feeling of the mind stretching, of comprehension approaching its limits and finding there not frustration, but something else, an openness, a receptivity, a particular kind of pleasure in the encounter with something genuinely larger than our current understanding. The cosmic web produces wonder. I don't think this is a personal quirk or an aesthetic preference. I think it is the appropriate response to something that is genuinely, measurably, almost incomprehensibly vast and intricate and old. Wonder is also, it turns out, one of the more reliable predictors of well-being in the psychological literature. Experiences of awe and wonder are consistently associated with increased feelings of connection, reduced feelings of self-focused anxiety, greater openness to new ideas, and a kind of expanded sense of what's possible. This makes sense if you think about it. Wonder, by definition, involves a relaxation of the boundary between the self and the larger world, a momentary experience of being part of something bigger than oneself. The cosmic web offers this in an extreme form. Nothing about it is bounded by any human scale. Nothing about it is familiar in any ordinary sense. It is, in every dimension, larger and older and stranger than anything else we've discussed. And encountering it, even approximately, even through the imperfect medium of words and analogies, can produce something in a person that is genuinely valuable, something that a quiet, ordinary Tuesday morning cannot quite produce, something that only encounters with genuine vastness can provide. I think that's one of the things stories like this one are for, not to convey information, though they do that when they work, but to create temporarily in the listener or the reader something like the appropriate response to the actual scale of the universe, to produce, even briefly, even imperfectly, something like the wonder that the universe encountered honestly deserves. Section 20. What remains unknown. We are close to the end of the night, and I want to spend a moment with what we don't know, because honest engagement with what is genuinely unknown is, I think, one of the most valuable things that stories like this can offer. We don't know what dark matter is. Despite decades of theoretical work, many experimental searches, and increasingly sensitive detectors, the fundamental nature of dark matter remains unknown. This is not a minor gap. Dark matter is the dominant form of matter in the universe, and it is the primary architect of the cosmic web. Not knowing what it is means not fully understanding the structure of everything. We don't know what dark energy is. It makes up 68% of the universe's energy content and is driving the accelerating expansion of space. The leading theoretical description of it, a cosmological constant, an energy of empty space, is consistent with observations but explains almost nothing about why that energy exists or has the value it has. This is, by some measures, the largest unresolved problem in theoretical physics. We don't fully understand the details of galaxy formation. We understand the broad strokes: dark matter, halos forming, gas cooling and collapsing, stars igniting, feedback from stars, and black holes regulating the process. But the detailed physics of how real galaxies get their shapes, their star formation histories, their sizes and masses is still actively studied, and many aspects remain uncertain. We don't know whether the cosmic web extends beyond the observable universe. The observable universe is the region from which light has had time to reach us, bounded by the cosmic horizon, beyond which we simply cannot see. Whether the same web-like structure continues beyond that horizon, and if so, for how far and in what form, is genuinely unknown. The universe may be much larger than the observable part. It may even be infinite. We don't know. We don't know whether the cosmic web is unique to our universe. If there are other universes, a possibility raised by some theoretical frameworks but not yet confirmed by any observation, they may have different physical laws, different initial conditions, different large-scale structures, or no large-scale structure at all. The web as we know it may be one realization of one set of physical conditions in one universe among many, or it may be the only such structure that has ever existed. These are not failures of science. They are the current frontier, the places where our understanding gives out, where the questions are real and important and not yet answered. The fact that these questions exist that they're being actively investigated, that the tools to approach them are being developed, is itself part of the story of what human minds are capable of. Section 21. The long view. Let me take the longest view I can tonight and see where it leads. The universe began, as we discussed, approximately 13.8 billion years ago. In the first fraction of a second, the fundamental forces and particles came into being. In the first few minutes, nucleosynthesis produced hydrogen and helium. After 380,000 years, the universe became transparent and the cosmic microwave background was released. After a few 100 million years, the first stars and galaxies formed. Over the next several billion years, the cosmic web developed its characteristic structure. Galaxies formed, merged, evolved. Stars lived and died, producing and scattering the heavy elements needed for planets and, eventually, for life. About 4.5 billion years ago, our solar system formed. About 4 billion years ago, life appeared on Earth. About 3.5 billion years of biological evolution followed. About 300,000 years ago, anatomically modern humans appeared. About 10,000 years ago, agriculture and the first civilizations emerged. About a century ago, we discovered that the universe contained other galaxies. About decades ago, we discovered the cosmic web. And tonight, you are here, lying somewhere in a small, particular corner of the web on a small planet, orbiting an ordinary star in a modest galaxy, in a small group, near the edge of a supercluster, embedded in a filament. And you know about all of this. In some approximation, the shape of the largest thing that has ever existed. This is not a common thing. In the entire 4 billion year history of life on Earth, in all the billions of species that have existed, you are part of the first generation, the first species, as far as we know, to have this knowledge. To know what the universe is shaped like at its largest scales. To know that the web exists. I don't say this to inflate the importance of any individual. The knowledge belongs to the whole endeavor, to centuries of astronomers and physicists and mathematicians and engineers and philosophers whose accumulated work produced the picture we have. No single person understands all of it. No single mind holds the whole picture. But collectively, we do. Our species does in this particular moment of its history. We know the cosmic web exists. We know roughly what it looks like. We know how it formed. We know what it's made of in the broad categories of its components. And we know what questions remain. That is an extraordinary thing to be part of. Even if all you've done is lie still in the dark and listen. Section 22. Coming home. We have traveled very far tonight, further than it's possible to measure in any human scale. We've been to the filaments that stretch for billions of light years. We've been to the centers of galaxy clusters, with their giant elliptical galaxies and their superhot X-ray gas and their supermassive black holes erupting in jets of energy. We've been into the deepest voids, where almost nothing exists for hundreds of millions of light years in every direction. We've been to the boundaries of the observable universe, where the evidence of the web thins into signals our instruments can barely detect. And now, as we always do, we come home. Home is this room, this particular room, wherever it is, in whatever country, at whatever hour. The surface beneath you is solid, reliable, real. The air around you, the particular temperature it is right now, carrying whatever it carries, the familiar darkness, the familiar quiet, the familiar sensation of a day coming to its end and a night offering, if you let it, something like rest. Your body lying here, doing what bodies do, breathing, circulating, maintaining, persisting, made of atoms, forged in stars, part of the cosmic web in the most literal physical sense, the most recent local arrangement of material that has been part of this universe since its beginning, organized for a brief time into something capable of knowing about its own existence and its own cosmic address. This is where all the vast distances come home to, not to an abstraction, to a body lying in a room at the end of a particular day on a particular planet in a particular moment of a 14 billion year story. And that body, that room, that moment, despite their smallness in the context of everything we've discussed tonight, are real in the same way that the filaments and the clusters and the voids are real. They are part of the same physical universe, governed by the same laws, made of the same material. They are not separate from the cosmic web. They are the cosmic web at a particular location and scale. The universe is not out there, separate from you, a backdrop against which your life plays out. You are in it. You are made of it. You are, in the most literal sense, part of it. Section 23, the thread back to your hand. Do you remember where we started? Look at your hand. We asked you at the very beginning of this story to look at your hand, to notice the lines of the palm, the texture of the skin, the way the light in this room falls across your knuckles. And then we told you that every atom in that hand was forged inside a star. Let's follow that thread one more time, now that we have the full picture. Those atoms were forged in stars. The stars existed in the Milky Way. The Milky Way is part of the local group. The local group is a small member of the Virgo supercluster, which is itself a part of the Laniakea supercluster complex, our cosmic neighborhood, 500 million light years across, containing 100,000 galaxies. Laniakea is a node in the cosmic web. One node among countless others distributed across a filamentary network that spans the entire observable universe, 93 billion light years across, containing 2 trillion galaxies, built from dark matter and ordinary matter, organized by gravity, operating on density fluctuations present since the first fractions of a second of the universe's existence. And your hand is made of atoms from stars that were part of that web, not metaphorically, not as a figure of speech, literally. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of every molecule in your cells, all of it was produced in stellar nuclear reactions, in stars that were embedded in the dark matter structure of the cosmic web, in a galaxy that is still embedded in that structure now. You are the cosmic web, looking at itself through a hand. You are the oldest light in the universe, arriving after billions of years at something capable of noticing it. You are the tiny fluctuation from the very beginning of everything, amplified by gravity over 14 billion years, organized by evolution over 4 billion years, into a mind that can, lying in the dark at the end of an ordinary day, ask what the universe is shaped like. That is not small. That is not trivial. That is not a thing that happened everywhere in the universe, or even as far as we know, anywhere in the universe except here. That is extraordinary. Section 24. A quiet thought before sleep. I don't want to end this story with numbers or with structures or with the vast impersonal machinery of the cosmos. I want to end it with something smaller, with the particular quality of the air in this room tonight, with the specific texture of wherever you're lying, with the breath moving in and out of your body. This body right here, this arrangement of atoms that has been traveling through the universe since before the solar system existed. The cosmic web will continue long after tonight. The filaments will continue feeding the clusters. The voids will continue expanding. Dark energy will continue accelerating the expansion of space. billions of galaxies will continue their slow motion through the web, drawn by gravity toward concentrations of matter or pushed apart by the growing distances between them. All of that will happen without your attention, without your effort, without any need for you to be awake for it. Tonight, you don't need to hold the cosmic web in your mind. You've been here with it for a while, and that's enough. Let it go now, the way you let go of the day. Let the vast distances fold back into whatever part of your mind they came from, and feel instead just the immediate, the near, the particular, the small, the weight of your own body, the quiet of the room, the simple ancient miracle of being here briefly as a thinking thing in a universe that is mostly made of things that don't think. The web is still there. It will be there when you wake up. It will be there for billions of years. The largest structure that has ever existed is not going anywhere. But you here now, in this particular arrangement, on this particular night, that is what's precious. That is the part of the story that is happening right now, and that will not happen again in exactly this form. The web made you possible. The stars gave you your atoms. The long history of life on Earth gave you your mind. And all of it, all the way back to the first instant of the universe, has been leading, in some sense, to this. A mind at rest at the end of a day in a room somewhere in the web, ready to let go for a while. That's enough. It has always been more than enough. Section 25. The last thought, as we close tonight, finally, gently, after this long journey, I want to leave you with something simple. Above you, the sky, whether you can see it or not, whether clouds cover it, or the light of a city washes it out, or the roof of a building stands between you and it, the sky is there, and beyond it, space. And in that space, in every direction, the cosmic web, filaments stretching for hundreds of millions of light years in every direction, clusters of thousands of galaxies at the nodes where filaments meet, voids hundreds of millions of light years across, almost empty, vast, beyond any imagining. And through it all, the ancient, invisible scaffolding of dark matter, the dominant form of matter in the universe, holding everything together in the structure that has organized the cosmos since nearly the beginning. All of it real, all of it there, right now, above and around and in every direction, the largest thing that has ever existed, continuing its patient, ancient evolution, regardless of whether any mind is awake to notice it. And in the middle of all of that, not the literal middle, because the web has no center, but the middle in the way that matters there is this planet. And on this planet, this night, and in this night, this room, and in this room, this breath, your breath moving in and out quietly, the way it always does, the way it has always done, the way it will do again all through tonight without you needing to think about it at all. You don't need to do anything now. The web does not require your attention. The universe does not need you to hold it together. It's been holding itself together for nearly 14 billion years without any help from any mind. All you need to do is rest. Let the day go. Let the vast distances go. Let the enormous numbers and the incomprehensible structures dissolve back into the background and feel only what's immediate and near and real, the surface beneath you, the air around you, the quiet settling of a body at the end of its day. The cosmic web will be there in the morning, old and vast and patient and completely indifferent to the hour. But you, here, now, in this particular night, that is the rare thing. That is the thing worth noticing before you close your eyes and let it all go for a while. Sleep well tonight. You are made of stars. You are part of the web. And right now, that is enough. Sleep sequence, the web at rest. And now, slowly, we come to the end. Not the end of the cosmic web that will outlast this night this century, this civilization, many things that currently seem permanent. But the end of tonight, the end of this particular journey through the largest structure that has ever existed, let's bring it back slowly from the scale of superclusters and filaments and the observable universe, bring it back through all those intermediate scales all the way to here. The cosmic web spanning billions of light years, the Laniakea supercluster spanning 500 million light years, the Virgo supercluster, the local group, the Milky Way galaxy, 100,000 light years across, containing hundreds of billions of stars. Our solar system, our star, our planet, the atmosphere above you, thin and protective, holding the warmth in, deflecting what should be deflected. The ground beneath you, solid and patient as it always is. This room, this moment, and yet you are aware of the web. You are part of a species that, in the brief moment of its existence, managed to map the structure of the observable universe, detect the dark matter that shapes it, simulate its evolution on computers, and understand, at least partially, what it is and how it came to be. The web has produced, in at least one location, something that can understand the web. That is a remarkable thing, not the most remarkable thing the universe has done necessarily. We can't know that from where we are, but remarkable. And it happened here, on this planet, in this species, in you, in some small part tonight. Let your breathing slow. The cosmic web doesn't breathe, it expands slowly, continuously, at the rate of a universe that cannot be stopped. But you can breathe, slowly, in and out. Let the weight of what we've talked about tonight settle, not as a burden, as a perspective, a reminder that you are part of something genuinely vast, genuinely ancient, genuinely structured in ways that took almost 14 billion years to produce. The filaments are still there. Tonight, while you sleep, they will continue to draw matter toward the clusters, expand the voids between them, evolve in ways too slow for any living thing to perceive directly. The dark matter that shapes everything remains in place, invisible, influential, holding the web together. The universe expands, as it always has, as it always will. And in one small location on a small planet, around an average star, near the edge of a modest galaxy, in a minor node of the cosmic web, something that emerged from the web is resting, getting ready to sleep, carried, without knowing it, in the gravitational embrace of structures hundreds of millions of light years long, connected through matter and time and physics to everything else that exists. You don't have to hold any of this in your mind to fall asleep. The web doesn't need your attention to continue. It simply does. As it has, as it will. Let your thoughts drift slowly, gently, the way matter drifts along a filament. Not quickly, not urgently. Just following the slow pull of something patient and ancient towards stillness, towards sleep. The cosmic web surrounds you tonight, and it is very, very quiet. Sleep well.